Okay, welcome back. So in the following, I want to dig a bit more into detail again into this good data science practice, which means like how to evaluate models and model selection and so on and so forth. I already mentioned it during the other discussions, but here again, the big picture, how you should approach like the design, model design or model selection in machine learning. So how does it look like? So usually you get a bunch of data. Let's say we are still in the supervised setting. And the first step you should do is you should take apart some test data. And please don't touch this test data anymore until the very, very end. Okay? And then what is left is, we called it here the learning set. There's usually not a standard term in the literature, but we may call it here learning set to make it more specific. This set you can use to do whatever you want, so to say. Okay? And usually what we do is we split up this learning set into one actual training set and one validation set. Okay, so this training set is then used to construct different models, right? We can construct a decision tree of depth 1, a decision tree of depth 20. We can construct a KNN classifier with k equals to 10 or k equals to 20 or whatever you feel makes sense. So you can construct various models. And then, as you have seen, is you're using this validation set on this model, for example, on the decision tree, right? And you get some predictions. And these predictions you can use as a feedback to your model construction, so to say, because you might see, okay, a decision tree of level 1, so of depth 1 is not good enough, all the predictions are wrong, so you should potentially increase your depth of the tree. So you make it deeper, and then, okay, you see, okay, it's still good, so you apply it, you see the prediction is still good, and so on and so forth, until you see you're reaching some overfitting regime, so you should potentially stop and you have found a good model, okay? So here, this block is essentially, we call it here the model builder block. So here you can play around. You can tune parameters, you can select different approaches, KNN, decision tree, neural network, support vector machine. You can really play around whatever you want, so to say. And once you have then make your final decision, right, you see that this decision tree with this size is the best, you can finally deploy this model. And the important point is, only at this point, only once you can now use your final test set to make your final evaluation to see whether this model really works. Okay, so that's a very important point. So the important point is that this here, this lower part, can only be executed really once, and you are not allowed to use this result here to draw any conclusions on the model building phase, right? You can't say, oh, wait a second, all of a sudden on the test set, I see that the predictions are not good, so I should play around here again and again, right? So this is not a proper way of doing this. So the only choice to pick here model is based on the validation set, right, and not on the test set. So please be really aware of this, because there are, I would say in the research, some directions where people are doing this wrong. They're essentially overfitting or over-engineering to the test set to make sure that here at the end of the day we get good predictions, but essentially what they're doing is they are leaking information from here to this model building phase, and this is what you should never do. So why should you not do this? Think about again that you are founding a company, right, a startup, and you want to really use machine learning in your actual product, meaning you want to apply it to unknown data, right? So if you would now cheat and say, okay, I'm using my test set and I'm playing around to get here good predictions, then your test data is not really a proxy anymore of your unknown data. Right? Because for the unknown data, you don't have labels and you don't know how this will look like, right? And if you're now cheating and using the labeled information, which you would have here to improve in hyphens your model construction, then this is actually what you, that you are somehow leaking information from the future to your model construction, right? Because this is the data you will see tomorrow, and tomorrow is not what you can use for constructing a model today, so to say, right? So in practice, there is no loop from here to here, assuming that you don't start annotating new data, right? But let's say in general, right, there is no flow from here to here because this is tomorrow and this is today. So please be very careful, because otherwise you get a false sense of performance of your model, right? You see, okay, here actually performs nicely and well, but just because you have cheated, right? So please, again, one more time, because it's so important, only use the test set once at the very end to report the final performance, and don't leak any information back here. This would be cheating, and that's very dangerous. Okay, so that's the good way of doing data science and how you should do model selection, how you then prevent overfitting. Another principle is k-fold cross-validation. So far you have seen the split of your given data and train, validation, test. In k-fold cross-validation we essentially generalize this. So we have here our test set which we split away. But then instead of having just one validation and one training set, we do these k different folds, meaning here we have another validation set and the rest is training, and another validation set and the rest is training. Meaning every part of the training data, of the learning data here, becomes part of the validation set, right? So here this part, then this part, and then this part. So why do we do this? We do this to do a better model selection, a more stable or more significant result here, meaning that we get rid of a bit of randomness in our splits, for example. What I mean with this is the following. So let's say you want to decide on the depth of a decision tree. Let's say this is your parameter you want to tune. Do you want to pick a decision tree of depth 1, 2, or 3? Instead of just using this validation set to assess the performance on this training set, right? So we build here the decision tree of level 1, assess the performance. Build here the decision tree of depth 2, assess the performance. We repeat this for every fold, meaning, again, here we also build the decision tree of depth 1 and assess the performance. Here we build the decision tree of depth 1 and we assess the performance. And then we average across these, okay? So for every fold, we do the corresponding training, right? So here, all these different decision trees. And then, for example, we can average the error we are getting. So we see what is the average error when we use a decision tree of depth 1. What is the average error when we use a decision tree of depth 2? Okay. And as you see already, because we're using this average, we get a more reliable and more significant result. Okay. So based on these three different steps, we can, for example, tune which kind of hyperparameters we want to use. By the way, the hyperparameters, this is a term we will see later on again in more detail. These are parameters we don't really train. So training, for example, in decision tree means that we train what kind of split we are doing, right? We are deciding, do we split on feature 1 and 2, and what is the threshold of the split? So this is what we are learning, training during our model construction. The other parameters, like K and KNN classification, or the depths, for example, in decision tree, these are hyperparameters, so one level higher, so to say, which we don't train, but which we, so to say, manually tune based on this validation set. Okay, so this is the notion of a hyperparameter. Okay, so we do this k-fold cross-validation to average out, so to say, this error to get a more reliable selection here. And in some cases, we can even average the model itself. This is not always possible depending on the model, but in some cases we can even do this. So the main point, however, again, is that we pick, or that we try to pick good hyperparameters, depth of the tree, K and N classification. And once we have decided on this, so let's say we have seen, okay, decision trees of depth 2, for example, are the best, then what we should do at the end is to use again all data here, so the full learning set, to train one more time, for example, a final model, or to at least inject the full data to your decision trees you have constructed, that the regions in the lower part contain all data. Meaning, if possible, we want to use this full set here to build our final model, because the more data we have, the better is the performance. Okay, so again, this is used for picking the hyperparameters. Level 2 decision trees are the best. And then here we train, for example, a level 2 decision tree. Okay. So that's the concept of k-fold cross-validation. Just very quickly, there's one extreme case, so to say, of this, which is called leave one out cross-validation. So the core idea is simply that the validation set is always one single instance. Okay, so here, this validation set is one single instance and the rest is the training data, which accordingly means, since every instance usually should be part of a validation set, we have n many splits here. Okay, so if we have a learning set of size n, we would have n many folds, because the validation set is always one instance and the rest is a training data. Next instance becomes validation, rest is training. Next instance becomes validation, rest is training. Okay, so this is specifically useful or helpful if your learning set is rather smallish, right? Because then you don't want to split away a huge portion for the validation set, right? Because then you're losing too much information from your training, right? Remember, here's your training, validation, and here's your test, right? If your training data is too small, then you can't really train a good model. And in this case, it's good to make the validation set rather small, right? But of course, if the validation set is only one instance, you shouldn't just do standard train validation test split. Then you should do leave one out cross validation, because you have to average the overall performance. Otherwise, it's getting too unreliable. Okay. So leave one out, an extreme case of k-fold cross validation. Big drawback, as you can imagine, this is extremely expensive because you have to train n many different times. So usually it's much better to stick to k-fold cross-validation, and a rough estimate rule of thumb is 10. 10-fold cross-validation, I would say, is the default, and which is a good trade-off between efficiency, right? Because you have to train 10 many models always, and reliability or significance of the selection you're doing at the end. Okay, good. So then quickly back to decision trees, because that actually was our main discussion here in this video. So we wanted to talk about decision trees, and we want to now also see how can we do this model selection. I said all the time here, we stop when we construct decision trees of level 1, 2, or 3. And indeed, there are different ways of deciding how to stop or when to how to grow this decision tree, right? Remember, you start at the root. You do the best, you find the best split, you split it up. You recursively repeat, right? And there are many, many different ways of when to stop, right? Or when to grow this tree, so to say, right? You grow it deeper and deeper. And one way, for example, is what we said a couple of times already, is when it's pure, when the region is pure. Not a good idea, as we said a couple of times. This will likely lead to overfitting, right? Because might work on the training data, but for the validation data, it might be too specific. So this is usually not a good idea. We can do this, what I said a couple of times now. We can stop when we reach a specific depth, 10, for example. We can say when the number of samples in a specific region is below a specific threshold, like at least 10 samples per region. We can talk about these gains we set, right? So delta I was the gain in the Gini index, for example. When the gain is too small, smaller than 0.01, for example, we can stop. Or we can use the validation set already that we measure accuracy on the validation set, right? So we can always see how good is it, or how good is it still? Do we already have overfitting? And once we see the accuracy on the validation set decreases, we just stop it. So these are just different principles, and in many of these frameworks on libraries like scikit-learn, for example, where decision trees were implemented, you can control many, many different parameters. So often you can specify all of these at the same time, and then you have different kind of ways to parameterize this. But remember, these are then again all hyperparameters, right? So how many instances? What is the threshold here? Maximum depth. These are all hyperparameters, and how do you pick them? You have to do k-fold cross-validation, for example. This is one way of doing this. These like a priori defined heuristics. The other one is so-called pruning, and I also quickly want to talk about this. This is just another principle. You first essentially build a tree until it's perfectly pure. So more or less you follow this rule, right? You build it until it's maximal and it's perfectly pure, for example, and then you do a post-pruning, right? So this is a priori defining some characteristics until when you stop, and here it's first constructed until maximal size, so to say, and then you do some pruning later on. There's one very prominent principle which is mainly used, which is the so-called reduced error pruning, and looks like the following. I go here step by step. So let's say you have your decision tree, right? Built until maximal size, and you have a specific inner node T. Okay. So what you can do now is you can first of all look at here this here the subtree, right? TT is denoted this blue subtree, and you can also look at the tree without the subtree. So the subtree pruned away, so to say. You see that this is the tree which is left when we have removed this part, so to say. Okay. So this is what we denote as a pruning. So T without T, small t, is this pruned tree, right? So of course you see that this is a more complex model and this is a simpler model, okay? So what we can do now is, for example, so we can use again our validation set to get some error estimate. So we can get the error estimate on on the full tree, and we can also get it for every pruned tree, right? We can test what happens if we essentially cut the tree here, right? So we remove this part. What happens if we cut it here? What happens if we cut it here? And of course, in practice, the trees are much larger, so there are many, many choices. So for each node, essentially, you can calculate the error, the validation error from the validation set on this reduced pruned tree. And you do the selection, again, in the greedy fashion for the subtree, which has the highest gain in the error, right? So you see, for example, if I'm cutting away this part, the error reduces from 90 to 85. If I'm cutting away this part, it only reduces from, so it's the error, right? So the error shouldn't be 90 actually. So if the error was 10%, you see it decreases from 10 to 5% error. But if you cut here, it reduces from 10 to 8 only. Then of course you would do this kind of cutting. You would prune to this tree, okay? So the tree which leads the highest error reduction is picked, and then you can just repeat, right? So this is a reduced tree, and you recursively do this. What happens if I cut here, if I cut here, and so on and so forth. So this is essentially the opposite of what we have seen for the growing phase, right? In the growing phase, we have started top down, and we split and split and split until we are more pure and pure and pure, right? And now in the reduced error pruning, we check for every possible node what will be the gain when we remove it, right? And then we remove it, and then we do this with the other ones, right? The difference here is that here, this is the important part, we do this for every node here, right? We have already constructed the full tree, and then we are testing everyone. This is not now a greedy heuristic in the other sense, right? It's not like we're just going backwards, but we're really testing every node, and then we are picking the next one. Then again, every remaining node, and then the best one, okay? But it's still some kind of a greedy heuristic, okay? So here again, one point. So after we have pruned a tree, of course, at the very end, we can again merge together test and so training data and validation data to build our final tree. But here, building doesn't mean that we construct a new tree, because then the purpose of this pruning would be gone. But we just do this for the region. So remember that every leaf node corresponds to a specific region, right? Here, specific instances here and here. And then what we can do at the end is we inject the validation data in this tree, right? So we inject the validation data to the specific regions that we get here higher counts, that we get more support in these regions. So hopefully better result at the end, okay? But of course, if we do reduced error pruning, we should not retrain our model, because then the pruning doesn't make any sense anymore, right? So we first, we could, for example, first apply, or we specify one of these heuristics, we build the tree maximally, we post prune it, but then we are stick to these decisions we have made, right? Then we can't retrain. Okay, so this is reduced error pruning, also very famous. And again, it's often specified in these frameworks. Let me actually just write it down. Scikit-learn is, or sklearn often also called, is one very famous machine learning library in Python, which is quite easy to use. So if you want to play around with non-deep learning neural network models, I guess sklearn would be a good starting point for you to play around. Okay, and then just some final words on this topic. So we have seen so far decision trees, or mainly talked about numerical features. At the very beginning, actually, we started with categorical features with this 20 question game. And of course, you can also do this in the tree growing phase, in the tree construction phase, right? Our example from before with playing tennis. Here, the names which are implementing this are ID3, C4, 4.5, so or card. So these are essentially just different variants how these categorical features are treated, because they're essentially on a high level two different ways. If you have categorical features, you can either ask yes and no questions. So is the outlook overcast, yes or no? Or you can do like asking for the answer. What is the outlook? Sunny, rainy, cloudy. Okay. So this would always lead to a yes and no branch, a binary branch. The other one can have an arbitrary branching factor based on the possible outcomes. But this is more or less the important difference. And then we mainly now talked about classification, right? We have these regions where we have different class proportions. But of course, you can also use decision trees for regression. So where we have like continuous targets rather than discrete targets. How does that work? So there are two important points. The splitting decisions are somewhat different, and of course the decision and the leaf node are different. Okay. So let's talk about first the regions. So if you at the end of the day end up in some region, so let's do it in a 2D, how we have seen it before. So here's our space, and let's say you split here and you split here and here and here, for example. So what can you do is, if you have this region and you are doing regression, of course the one easy way would be to compute the average, the mean of this region, right? Remember, every of these samples here now has not a class label, but it has a different number, right? So here, for example, is one with 8, here's someone with 7, here's someone with 6, right? And here's someone with 1, here's someone with 3, and again a 1, for example, right? So the targets are numerical values, and so it would make sense to use, for example, as a predicted value, the mean of the region, okay? So the leaves compute the mean instead of the mode, so the majority class is the mode. We use the mean here as our predicted value. That's one difference, while in the leaves we do this decision. And then the other difference is, of course, how do we decide on a split? Because so far what we did is we tested every possible split threshold, and we computed the Gini index, for example. But the Gini index requires categorical values. So what can we do, for example, for real values? We can, for example, compute the mean squared error as a splitting heuristic. So what does this mean? It means, for example, that let's say we have here this space here, and this is now like a one-dimensional input, and here we illustrate the output. So this is a prediction. So please don't confuse this plot with this plot. These are very different things, right? This is a 2D space, and the prediction is here illustrated by these numbers. This is a 1D space, and the prediction is illustrated here. Okay, so we can only split in one feature anyways here. Okay, and here actually you see the split, right? So you see here that, for example, here we have a split, and here we have a split, and here we might have a split based on the depths, and here we have a split, right? So we have all these small blocks. And let's look at one block, for example. One region is here, one interval, so to say, as set, right? If this is our region, let's actually try to shade this. So let's say here's our region, which is now this interval here, right? This is our region. The prediction is like the mean, which is illustrated here by this line, right? This would be the mean of all these points in this region, in this interval, right? And we can, for example, use the mean squared error as a measure how good, how pure this region is. So mean squared error could mean, for example, we measure how much does this instance, so yi, deviates from the corresponding mean in this region and then summed up over the instances, okay? So we're measuring how much does this instance deviate from the mean? How much does this instance deviate from the mean squared, and we sum it up, for example. And of course we could normalize divided by the number of instances in this region, let's say, okay? So this would be one possible measure to measure the goodness, the purity, so to say, of this region, right? If all samples are close by to the mean, so let's say here, for example, this region here, right, which are these samples here, they are all mainly close to the mean, so the mean squared error would be small. It's a good result. Here already we have some deviation, so the mean squared error would be larger, so it might be useful to split this region further, okay? So long story short, instead of Gini, we could use some other continuous valued loss function or error function, which would be like this mean squared error. So the deviation of the instances to the predicted value, which is here the mean, okay? Otherwise, the rest is the same. We can do this greedy growing heuristic. We can do this pruning, for example, and then we can just use decision trees for regression as well. Okay, so some higher level discussion on this on these decision trees. So one big advantage of decision trees, and this is why they are so famous and widely used, is that they can be easily interpreted, right? We used this actually already in our discussion how we started, right? At the end of the day, you have this nice tree where you have these kind of tests at the inner nodes, and these tests can be looked at from a human perspective, right? I can see, okay, feature 1, outlook, should be sunny, or like the income should be larger or smaller than some specific value. So this is one of the biggest advantages of decision trees compared to many of the other models you will learn in the lecture. They are quite easy to interpret. This is a big pro, specifically if you think about applications where interpretation might be crucial. If you think about like insurance applications, for example, or some other critical medical applications, interpretability might be a very important point. And this is here ensured by decision trees. Another point is it can easily handle a combination of numerical and categorical features. So the split can ask these questions like for discrete values or for continuous values. It doesn't matter. We can just mix and match, which is a bit harder in a KNN classifier because there we have to combine different distance functions. Distance functions for categorical and for numerical features, which is not so principled. Here, however, it's very easy. So there are a couple of extensions, which we actually will also later on talk about, specifically like random forest, which are extremely powerful. So they have won many Kaggle competitions. So if you're not familiar with Kaggle, this is like an online competitions for like, say, machine learning data science tasks. And indeed, many of these competitions were won by extensions of decision trees. So indeed, in practice, they are extremely powerful and they are frequently used. And if you don't want to go for neural networks, I guess decision trees or random forests are the way to go anyways. And then last but not least, compared to KNN, and we said it already during this video, they are much smaller in their memory footprint. We don't have to store our actual data, and they are also much faster in the inference time because we just have to traverse a tree. And we have, this is somehow debatable, I would say, more flexible decision functions. In decision trees, we have these rectangular regions. Right? In KNNs, we have some different kind of regions. Regarding flexibility, of course, in a KNN, you have all this choice of the K only, but in a decision tree, you have restricted to this KNN. So the decision function, in my opinion, might not be actually the main point. So potentially, I would even put it here into the brackets because the KNN also allows some flexibility, but again, a decision tree has much more control, so to say, also in the kind of parameters you can pick. Good. Okay, and then, as quickly said, we also want to talk about these extensions, but we also do it on a high level so that you know the basic terms, the basic concepts behind it. And if you want to know more details, again, please just do an online search and you will definitely find many videos and slides on these topics in more detail. The main point I want to mention here then is the concept of ensembles. So an ensemble is in principle a meta approach where we do the following. Instead of just having a single model, a single decision tree to perform our predictions, we have a multitude of models. We have many different classifiers, for example, which build our final prediction. It could be multiple decision trees, or it could be a mix of decision trees and KNN classifiers, or whatever you can think about. So the core idea of an ensemble is simply multiple models are used to make our final prediction, not a single one. And the main benefit is that this essentially reduces the variance in our predictions by averaging out. So we'll talk about this bias variance trade-off later on in linear regression in more detail. But you can already get an intuitive feeling, as we already said it for like k-fold cross-validation. Since you're making multiple predictions, multiple runs, so to say, you average out your predictions. This is more reliable, more stable, so you're reducing the variance of this, okay? So that's the main benefit of using multiple models at the same time. It's a bit of like, instead of just asking a single person for its opinion, you are asking multiple people for its opinion. Of course, then you get a more reliable estimate of what is really true, hopefully at least. And there are different ways of doing this: bagging, boosting, stacking, and so on and so forth. I will quickly mention these two because these are two terms you should have, you should definitely know about. So one is bagging, which is like the abbreviation for bootstrap aggregation, or aggregating if you really want to see the ing here. So bootstrap aggregation, which simply means you are building your models or your different models based on different randomly selected subsets of your data. Okay, it's a bit like relating to this k-fold cross-validation, if you can already see. But here it's very different, well, not very, but different, since you're really using then multiple models. Put differently, if you have your training data, you randomly sample, usually with replacement, so you put it back, subsample your data, And for all these different overlapping subsets, you train a model. And then once you have these, let's say 20 models, you can apply them during your inference time. So you get a new query, a new test instance. You feed it in all of these 20 models. You get for all of these models a prediction. And then, for example, you can use a majority vote or some average to form your final prediction. So very simple principle, very powerful. You just subsample with replacement your training data, and then you get just multiple classifiers. And the second principle is boosting, where you essentially train incrementally a chain of classifiers. Think about the following. So you have like your data set, and you train a specific classifier, and you see that for some instances the prediction is already correct, and for some other instances the prediction is still wrong. Okay, this could happen, right? Because we don't overfit to the training data. We want to generalize, so it can still happen that some instances are misclassified. Okay, what then boosting is doing is it's now training a second classifier, which is giving more importance to the so far misclassified instances. Okay, so one bunch is already correct, the rest was misclassified. So in the next iteration, I'm giving more focus on these and only less focus on the other ones, and I'm training a new classifier. You can think about, like, for example, re-rating these instances, right? At the beginning, everyone has the same weight. Every training instance has the same weight of 1 divided by n, let's say, right? Equally distributed. And then in the next iteration, we give higher weight to the ones which were misclassified and smaller weight for the ones which are correctly classified. And we train another classifier, which then focuses on these apparently, right? And we hope that then the second one will take care of the rest. And then we repeat this procedure, right? We again see what is now misclassified and so on and so forth. At the end, we have a chain, a multiple set of classifiers, an ensemble, and then this ensemble is then used to make the final predictions. So in more detail, a bit here for the decision trees. So this bagging idea combined with decision trees leads to the principle of random forest, which is the standard approach or one of the standard approaches of machine learning in practical applications, random forest. So it's really back decision trees. So we look at a subset of the data. There's one trick here, one potential other idea is that these back decision trees are often extremely correlated actually. As you can imagine, right? If you just pick subsets of the data, these trees might be rather similar. So what actually random forests are doing is they increase the diversity of the classifiers, but also subsampling the features. So you can think about that we are doing a bagging not only on the instance level, but also on the feature level, okay? So if you think about it like the following, let's say you have a data set, right, X, where you have here feature 1, feature 2, feature 3, and feature 4, like the attributes like age, income, hobby of a person. And here you have the axis, so the actual instances, different people, right? So what a random forest is doing is it randomly subsamples instances, right? We take this instance, this, and this instance, for example, and it randomly subsamples features, this one and this one, for example. And based on this smaller subset, it constructs a decision tree, okay? And then it repeats. Different subset of instances, different subset of features, it constructs a decision tree. And then we get a nice ensemble of decision tree classifiers. All these are considered at the end together, and we do, for example, the prediction via a majority vote, right? So we have here constructed T1, T2, and T3, right? Let's say we get a new instance X. This one says blue, this one says blue, and this one says this orange. We could, similar to like a KNN classifier decision, we can say, okay, now this instance apparently is most likely blue based on the outcome of this ensemble of trees, okay? So as said, this is often used in practice, works quite well. Of course, it's a bit less interpretable than a standard single decision tree, right? Because you do not have one, but you have many. And indeed, in practice, you have lots. You can have hundreds of trees. So you're losing a bit the interpretability to some degree. But the good point is that the number of random forests, so the number of trees in the random forest, or the rule of thumb, usually is like in this order, or a square root of d, so it's not exploding usually. So it's not small, but it's not very, very big at the same time. Okay, so this is the concept of random forest, and this just should give you here the high level idea of what this is about. And then lastly, Also the idea of boosting, right? What I already explained here is the following, and for decision trees, XGBoost is the most famous approach. Again, boosting is doing what I already explained. It's giving weights to the instances. It starts with uniform weights for every instance. Every instance is equally important. It trains this classifier. It increases the weight for the misclassified one, and then it retrains, or no, not retrains. It gets a new classifier with this importance increased for this one, and then we again get an ensemble. So the only difference between AdaBoost and this XGBoost, so adaptive boosting and gradient boosting, is essentially how these weights are calculated. AdaBoost has some closed form based on how this error looks like, the misclassification error. XGBoost looks at the residuals. So, for example, if the prediction is already very close, so to say, to the true label, then you get a rather small weight. If the prediction is very far away from the true label, then you get a larger weight, which technically can be computed based on the gradient. This is why it's called gradient boosting. It just gives you a different way of re-rating. But at the end of the day, the principle is the same. Once you have re-weighted it, you train another one, and you continue this process. And at the end, you have multiple classifiers, and every of these classifiers is a different weight. That's probably something you should know. It's not that all these classifiers, like here, they have the equal contribution, so to say, to the decision. But usually how it works is that the first classifier has most of the importance at the end, and the second one even less, because they are only focusing on the residuals, right? So you have then not a uniform ensemble, but you have a weighted ensemble where every classifier has some different importance at the end. Okay, so these two concepts are, let's say, enough to understand the high-level idea of ensembles. Here it's mainly focusing on subsets of data and features, and here it's focusing on misclassified instances by doing a reweighting. Okay, so that's then the end of this decision tree lecture. So just to wrap up again, what have we learned? So we have learned how to build a decision tree. First of all, what is a decision tree at all, right? And so how you can look at it, how you can interpret it, what these inner nodes and what this leaf means. We talked about specifically how to construct this tree by having different splitting heuristics, Gini index, entropy, misclassification error, which mainly are looking at the impurity of these regions, and then we grow it over time. Very important, we talked about overfitting, and in general about good data science practice, right? These problems you can see if your model becomes too complex or if it's too simple, and how you make sure that at the end of the day you can have a good model, right? Doing this pipeline of train validation test or even k-fold cross-validation. And lastly, we quickly talked about ensembles, where you can improve the performance of your models by having not just a single classifier, but a set of classifiers, and you construct these in various ways. So with this, we're at the end of this video. I thank you for your attention, and as usual, if you have any questions, feel free to post them online. Thank you and bye-bye.